All right, this is OXDF looking at day 12, Advent of Code 2021. I actually solved this one yesterday while sitting in the middle of an airport, so I couldn't record a video while solving it, but I thought I'd go back and probably make the same mistakes I made yesterday, so we'll give it a shot here and see how it goes. The challenge is called passage pathing. Basically, I'm going to get a list of connected cave rooms, and so you can go. This means you can go from start to A or A to start. A to C or C to A. So you can take this and make kind of a map that looks like this. And so the goal is to find the number of distinct paths from start to end that don't visit small caves more than once. So it defines, A is in all caps, so it's a big cave. B is in lowercase, so it's a small cave. So you can only visit each small cave once, but you can visit the big caves, A in this case, as many times as you want. So that's why you get things like start A end, start A C A end, start A B end, but you're never going to get start B D because once you go to D, you can't go back to B again, so you're at a dead end. It's not a path anymore. So that's what they lay out here. They show all those paths. They actually give us 3 different examples in this one. So here's another path. Again, you can see the big caves like HN and LN, and then the small caves. We've got 19 paths. This one has, because it's got more big caves, I think, maybe just more paths. It's got 226 paths. So the question is, how many paths can you go through your puzzle input visiting small caves at most once? All right, so let's jump over to Python. So normal thing here, got my template started, lines equals. So the first thing I need to do is run over my list of lines and I'm going to create a dictionary. And so I'm actually going to use a default dict for this one. And what that'll let me do, let's see. So I'll say paths equals default dict list. And so basically I'm gonna have this default dict. So if I try to reach something that doesn't have a key, it's just gonna return an empty list. And this is gonna be really convenient now because I don't have to check every time, does this key exist? If not, create it and then add something. And if it does, just add something. I can just work with it and add something to it. So now I'll group over my lines. And what I'm gonna do is I'm gonna say A comma B, just generic, my 2 things. Let's vim 12 example 1. And so all I need to do here is line.strip, because I want to get rid of the new line, .split on dash. And that should give me an A and a B. And then what I'll do is I'll say paths sub A dot append B. And paths sub B dot append A. And what this is going to do is it's going to create a dictionary for me, or a list for me here. Let's see, a dictionary. So Python 3, day 12, 12ex1 is what we were looking at. From collections, not from default dict, but import default dict. And let's add the dash I here so we can see what do we have now for paths. So you can see here, if I put in start, in fact, I can do that, paths of start, it can go to A and to B, and it matches what I have here. If I put in capital A, it goes back to start. It can go to C, B, it can go to the end, etc. And so now for any node, I can find out the nodes it can visit. I'm going to add a bit more logic here, and the fact that based on the fact that start is one you can never go to. So what I'm going to do is say if there should be no case where start is appended here. And there should be no case where end, you never leave end. So I don't ever want A to be end here. I don't ever want B to be start. So I'll say if A is not equal end and B is not equal start. Because if either of those is the case, I just want to ignore it. Do that. And then same thing here. If B is not equal end and A is not equal start, and do that. And I think that's all I need for there. Now, that'll just give me a little bit cleaner paths. Let's check it out. So basically now start goes to A and B, but A doesn't go back to start. You never go back to start. So that's what I want. And there is no end in here anymore. I used to have an end could go to A or B, but now I don't need that anymore. So that looks good. Okay, Okay, so how am I gonna traverse this cave? And this is a really useful case for recursion. I think I did a recursion in day 11 as well. So we'll define a function def walk, and we'll just have it say, pass in visited. And so what I'm gonna do is I'm gonna check the last element in visited. So if visited sub -1 equals end, basically I'm done. Let's just print visited. And then we will return. And so now, if I'm not at the end, if I'm in some cave, I want to see which caves can I go to. So I will do for cave in, what's my paths sub visited -1, like that. Get the last, so I get the last cave on my list, and I will see where can I go next. And I'll loop over each of those options. And so what I can do now is I can say, so if node, or not node, cave, if not cave in visited, that means I haven't gone to the cave yet, or cave dot upper equals cave. So basically, if it's an uppercase, because if it's uppercase, I'm going to go either way. And if it's not in the visited list, I'm going to go. Then I'm going to do walk of visited plus cave. So I'm just going to basically call the function again, and I'm going to go check out that cave. And that is it. I don't have any counting going on here, but I think that's all I need to start with, to at least get started on. Okay, so I never reached end here. I wonder why. Let's see. Oh, I never called the function. So the last thing I need to do, walk, and what I'll do here is I'll just say visited equal. That seems messy. Let's just come back here. And to start, I'm going to go into a list that just has start in it. Try that again. Clearly I made a typo. 23. Visted. Try that again. And cool, that printed out all these different paths I can go to get to the end. Let's see. I'm curious to know how long that is, because what in the end what I'm going to be looking for is a count. So I could just solve it this way, where I print all of them and print it into word count. 10 sounds like the right answer. Here it is. Yep, 10 paths. That looks pretty good. Just to show how I would count, I could literally just solve it now. In fact, so we could do example 2 is 19. Example 3 is 226. So example 2 is 19. Example 3 is 226. And so I'm looking for how many in my puzzle input, 4659. 4659. So I could just solve it that way. That works perfectly fine. But just when you're working with recursive functions, it's nice to know how to do this. So if I just called walked on end, if I started an end, then I want to return 1 here. And excuse me, that's a tricky kind of edge case for a second, but I'm going to return, in this case, I'm just going to return 1. In the other case here, where any case where I'm going into other caves, I'm going to start by keeping a count, start at 0, and then for each of these, I'm going to say count plus equals, the number of paths that go down that way. So if I start in start and I come in here, that's not going to happen. I'll go then loop over start, and start's going to go to A or B. And so when I'll go to A by calling walk on start plus A, and it comes back up here. And I'll come down again and I'll loop through, and one of the things I'll go to is visited of start A exit or end, and that'll return 1, which will get added to my count. Another one I'll go to is like start A B, which then itself will call exit, and that'll return up to here. And so that these things will loop into the count here. That's probably the hardest part of recursion to conceptualize. I'm not sure I'm explaining it great. But at the end here, I can just return count. So if it's end, return 1. If it's not end, try all the rooms that you can go to, and each time, collect all of the paths that came back, and at the end, return that count. And so with that, I can do print. Let's do double there. Part 1. Put that in there. Close you, close you. And now we no longer want the word count, and we get the same number. So we got our 4659. So I feel like that was probably not the best explanation of how you collect recursion, but it's worth playing with sometime if you ever want to see how that works. You could put some debugging and sort of step through this and see how things go. Okay, let's jump back over here. We're on to part 2. Now you realize actually, instead of not being able to visit any cave more than once, you can realize you might have time to visit a single small cave twice. And I misread this at first when I was originally solving this, went down a big rabbit hole. It's not you can visit each small cave twice. Once you visit any small cave twice, the rest of the rooms, you can only go, the rest of the small ones you can only go into once. It's also, they are very explicit here, you don't ever go to start again or to end again. So there are now 36 possible paths. So let's try this here. We're going to do something very similar. Let's see, come down here, yank this, paste. Don't want that anymore, so get rid of that. And we're just going to call this walk 2. And it's going to be very similar, but this time we're just going to change our logic a little bit. So walk, make that 2, make that a 2. Okay. So what is walk 2 going to look like? Well, if we're at the end node, we're in the same place we were before. We're done. Let's return 1 and move on. We're going to still loop over all of our caves. And this time, just the logic is going to get a little bit more, this if statement, it's this stuff right here we're going to change. So let's think through the different logic here. First of all, we can do if, I don't know why I was going to call this node. I think I must have called it that yesterday. Cave.upper equals cave. So if it's uppercase, I'm visiting. So right, count plus equals walk 2 visited plus cave, and that looks good. Else if, actually let's simplify here, and this will make it easier to follow if I just do an else. So now I know I have a lowercase node. Okay, let's find out how many times I've been to that node. How many times visited is equal to, I'm going to make a list comprehension here. So I'll do n for n in cave, not in cave, in visited, if n equals cave. So this will give me a list of all of everything in my visited string, but only if it's the current cave that I'm looping through. And so then if I do len, now I'll know how many times have I been to this cave before. And so if times visited equals 0, never been to that cave before, then no matter what, I'm going to go to it. So I'm going to say count plus equals walk 2 visited plus cave. Else, and not just else if. And this is where I need some way to track, have I visited, am I done with my extra small room? And so I'm going to actually add something here. Small done, else if not small done, count plus equals walk 2 visited plus cave, comma, true. And so we can close it off here. Get rid of this because I'm not using that at all. So I need to be able to track this small done. And so basically when I call it originally, I'm going to walk 2, comma, false. I've not done my small yet. And we'll put it up here in the, yep, we added it here. So now when we go here, small done is going to be the same as whatever it was before. So we'll just leave it. And same here, small done didn't change. because I haven't visited the room before, so I visited it for the first time. My little extra check is not complete. If I get to this point where I know it's a lowercase room, because I got to here, I know the times visited is greater than 0. So I visited it before, but I'm still gonna go. Then now I'm gonna say small done. My small done is true. So now any paths that come off of this will not be able to revisit So once it's small, if I visited it before and small done's already marked true, then just nothing's gonna happen. I'm gonna just keep looping over that. And so that's actually all I need there to finish, I think. Let's give it a try. Let's start with our test input. 36, was that what we were looking for? I think it is. 36 possible paths. Awesome. Let's see, so the next one is 103 and then 3509. 103, 3509, so it's looking pretty good. We'll do our puzzle input. It's quite long, but 148, 962, 148, 962, and that's where we get the stars. So again, this is a really cool example of the power of recursion. You could do this without recursion. The other alternative would be, as you loop over these paths, you still keep list of different paths you're going down, and you maybe create a queue somewhere. And so you just do a while queue, you add it to the queue, and then do a while queue, while this list of paths to check. And then you remove it from the queue, you loop through that while loop, remove the first one, add back. So let's see. So you might have a queue that looks like, you might have a queue it will start with start, right? And then you're going to remove start from the queue, and you're going to say, well, now I want to add start-A and start-B. Okay, let's go. So we have start. Then you're going to remove start-A from the queue. I don't know why I put that there. So you remove start-A, and at the end of the queue, you add start-A dash, and where can A go? I've already forgotten. Let's add this. There we go. Oops, I did not mean to be moving it. Minus I, paths sub A. So A can go to C, B, and N. So we're going to add C, start, dash A, dash B, and start, dash A, dash end. So now we'll try all of those. And then we'll remove start, dash B from the queue, goes back at the beginning of our loop, and we will add start, dash B, dash, and we come down here, and we find out, okay, dash A, start, dash B, dash D, and start dash B dash end. Okay, and then we come to the front and we remove our first one from the queue. So what can C go to? C can go back to A. So we will remove this from the front of the queue, and we will add start dash A dash C dash A, and our loop is done. And then we're back here. Where can B go? And we work through this, and eventually we're going to reach some at the end. Well, anytime we reach something that has end, we can put it into a different list, and we'll store that list, and the length of that list we will return. So I don't know if that was helpful to watch, sort of pseudo manually walking through this creation of this queue, but you can see how you can create a while loop and just keep going, and eventually this queue will reach an end point where you're not adding anything new in it, and it eventually goes down to 0, and then you'll have your list of ones that are done. So but I think recursion is just much cleaner there. And you can see, we solved this in really not that many lines here, even for the more complicated one, and the short one was much shorter. So anyway, thanks for sticking around to the end. Hopefully you enjoyed this challenge, and I will talk to you next time.